Hello friends, welcome to my lecture on normal distribution. The normal distribution is also known as Gaussian distribution and it is very common continuous probability distribution. It is very important in statistics and is often used in the natural and social sciences to represent real valued random variables whose distributions are not known. A random variable with a Gaussian distribution is said to be normally distributed and is called a normal variate. The probability density function of the normal distribution is given by f x mu sigma square, which is given by 1 over sigma root 2 pi e to the power minus x minus mu whole square divided by 2 sigma square, where mu is the mean or expectation of the distribution and also its median and mode, okay, because at the mean the mean, median and mode, okay, you can see in this figure they coincide, and sigma is the standard deviation. This is the figure of the graph of the probability density function of the normal distribution. Okay. So, this is the graph of the probability density function of the normal distribution. You can see that at x equal to mu, the function f x x assumes its maximum value, which is given by 1 over sigma root 2 pi, and it is a well shaped curve. Okay. It is a shape of the curve is well shaped. So, it is a well shaped curve. Okay. Mean, median and mode coincide for this distribution. Okay. Mu is the mean and sigma is the standard deviation. The maximum value occurs at x equal to mu, which is given by 1 over sigma root 2 pi. Now, the simplest case of a normal distribution is known as a standard normal distribution. In this case, what we do is we put here z equal to x minus mu over sigma. Okay. So, z equal to, when you put z equal to x minus mu over sigma, then what happens is the mean of the distribution for the standardized normal distribution is equal to 0. Okay. Mu becomes 0 and sigma becomes equal to 1. It is described by the probability density function 1 over root 2 pi e to the power minus half x square. So, here if you take instead of x minus mu over sigma z, then this becomes e to the power minus 1 by 2 z square, and the probability density function becomes 1 over root 2 pi e to the power minus z square by 2, or we can also write it as 1 over root 2 pi e to the power minus x square by 2. Now, this is the probability density function for the standardized normal distribution can be seen from here. This you can see that phi x is greater than or equal to 0 for all x. Okay. Phi x is greater than or equal to 0 for all x, which is the first condition for the probability density function. Second is that integral over minus infinity to infinity phi x dx must be equal to 1. So, that we can see here 1 over root 2 pi integral over minus infinity to infinity e to the power minus half x square dx. So, let us integrate this integral over minus infinity to infinity e to the power minus half x square dx. Since e to the power minus half x square is an even function, we can write it as 2 times 0 to infinity e to the power minus half square dx, half x square dx. Now, let us take half x square to be equal to t. Okay. So, then what we get 1 by 2 into 2x dx equal to dt. Okay. So, we get dx as dt by x. X is equal to root 2 t. Okay. So, 1 dt upon root 2 t. Okay. So, let us put it here. Now, when x is 0, t is 0, and when x is infinity, t is infinity. So, the limits remain the same, 0 to infinity, we get e to the power minus t, and for dx we put dt by root 2 t. Okay. So, what we get then, this root 2 we can cancel with here 2, and we get root 2 and integral 0 to infinity t to the power minus half e to the power minus t dt. Okay. Now, we can write the value of this integral by using gamma function. We know that integral 0 to infinity e to the power minus t to the power x minus 1 dt is equal to gamma x. Okay. So, here we have t to the power minus half, we can write it as t to the power half minus 1. So, this is gamma half. Okay. So, this is root 2 into gamma half. Okay. So, but we get then integral okay, thus we have found the value of this integral. Let us evaluate the integral over minus infinity to infinity phi x dx now. So, this will be equal to 1 over root 2 pi. Okay. And here we get root 2 into gamma half is root pi. Okay. So, root 2 into root pi. Okay. So, this cancels with this and this cancels with this and we get 1. Okay. Remember gamma half is equal to root pi. Okay. So, this integral over minus infinity to infinity phi x dx equal to 1 and therefore, we can say that this phi x is a probability density function when we replace x minus mu over sigma y z, which we have taken as x here. Okay. Now, we can also see that for this probability density function, okay, the standard normal distribution mu is equal to 0 and sigma equal to 1. So, let us find mu. Okay. So, mu is the expectation of the standardized normal distribution phi. Okay. So, we have integral over minus infinity to infinity. Okay. We have we are taking e to the power. Okay. So, x times e to the power minus half x square dx and we also have 1 over root 2 pi. Okay. 1 over root 2 pi is the multiple of so let me put it like this, x times this. Okay. So, x times the probability density function, which is 1 over root 2 pi e to the power minus half x square dx. Now, this is equal to 1 by root 2 pi. Okay. We have integral over minus infinity to infinity x e to the power minus half x square dx. Okay. Now, you can see that this is an odd function of x. Okay. This is an odd function of x. So, integral over minus infinity to infinity x e to the power minus half x square dx is equal to 0. Okay. Since x e to the power minus half x square is an odd function of x. Okay. Now, let us also find the variance of this. So, we need to find E x square, that is E z square. This is actually phi, we are writing here the z equal to x minus mu over sigma. Okay. X minus mu over sigma, z is the standardized normal distribution. So, we are writing E z square. This is actually E z. We can write E z here, exponential expectation of z. Okay, expectation of z. So, this is expectation of z square. Let us find. This will be integral over minus infinity to infinity. So, x square, we write x square, okay, e to the power minus half x square divided by root 2 pi. Okay. So, now this is 1 over root 2 pi. X square e to the power minus half square is an even function. So, we can write it 2 times 0 to infinity x square e to the power minus half x square dx. Okay. Now, let us put half x square equal to t as we have done earlier. So, then this will be x dx equal to dt. So, we shall get, and the limits of integration will remain 0 infinity. So, this is 2 over root 2 pi 0 to infinity x square is equal to 2t. Okay. X square is 2t e to the power minus t and dx is equal to dt upon x, that is square root 2t. Okay. So, this is equal to 2 over root 2 pi root 2t will cancel with 2t and will give you root 2t. So, root 2 here, integral 0 to infinity t to the power half, okay. T to the power half means t to the power 3 by 2 minus 1. So, this is like this we get, okay. So, this root 2 will cancel with 2 here, root 2 here, and we get 2 over root pi, and this is gamma 3 by 2, okay. This is can be evaluated from here 0 to infinity e to the power minus t, t to the power x minus 1 dt equal to gamma x, okay. So, this is t to the power 3 by 2 minus 1. So, gamma 3 by 2, which is equal to 2 over root pi 1 by 2 gamma 1 by 2, okay. So, this is 2 over root pi 1 by 2 square root pi, and this cancels with this cancels with this. So, E z square is equal to 1, okay. Now, variance of z is equal to E z square minus E z whole square, okay. This is E z. So, E z whole square. So, this is 1 minus E z is 0 we have seen, okay. So, we get variance as 1, variance is nothing but sigma square, okay. So, sigma square is equal to 1, okay. So, here we can see that mean is equal to 0 and sigma square equal to 1, or we can say sigma equal to 1. Now, this function you can see e 1 by root 2 pi e to power minus half x square is symmetric about x equal to 0, okay. We replace x y minus x, it does not change. So, it is symmetric about x equal to 0 where it attains its maximum value. It attains its maximum value at x equal to 0, okay, and it is 1 by root 2 pi. It has inflection points at x equal to 1 and x equal to minus 1. So, this we can see we have phi x equal to 1 by root 2 pi e to the power minus half x square, okay. So, let us find its first derivative phi dash x. So, 1 by root 2 pi we have e to the power minus half x square into minus half into 2 x. So, we get minus 1 by root 2 pi x e to the power minus half x square, okay. Now, let us find phi double dash x. So, minus 1 by root 2 pi and we have x into e to the power minus half x square into minus half into 2 x, okay, plus derivative of x, that is 1. So, e to the power minus half x square, okay. Now, what we get here? So, this is minus 1 by root 2 pi e to the power minus half x square we can write outside, and we have 1 minus x square here, okay. Or we can say e to the power minus half x square divided by root 2 pi into x square minus 1, okay. So, phi double dash x equal to 0 implies that x square is equal to 1, okay, or x equal to plus minus 1, because e to the power minus half x square is never 0, okay. It is never 0, it is in fact greater than 0, okay, for all x. Okay, so, if we have a differentiable function phi x which and it turns out that phi double dash x equal to 0, then the points where phi double dash x equal to 0 gives us the inflection points. What are inflection points? Inflection points are those points on the curve where the concavity of the curve changes, okay. So, you can see how it changes. So, x equal to plus minus 1 are the inflection points, inflection points, okay. Of phi x. So, if you draw the graph of phi x, it will look like something this, okay. This is your x axis, this is 0, x equal to 0, at x equal to 0 it assumes maximum value 1 over root 2 pi, and then it drops down, okay, and at x equal to plus minus 1. So, this is your the point x equal to 1, okay, where the concavity of the curve changes. It was downward earlier, now it becomes upward. Okay. So, let me write again. So, okay. So, here, okay, the concavity of the curve changes. This is minus 1 and this is 1. So, concavity of the curve changes and this is 1 over root 2 pi. This is your standard normal curve, we call it standard normal curve. Okay. So, you can see it is symmetric about the y-axis. Now, let us go further. The probability of the variate x, the normal variate, okay, the probability of the normal variate x lying between x1 and x2 is given by the area under the curve for 1, under this curve, okay, under the curve for 1, say x1 is here, x2 is here, okay, then the area under this curve from x1 to x2, okay, this area, okay. So, this area will give us the probability of the normal variate from x1 to x2. So, that probability is given by integral over x1 to x2 1 over sigma root 2 pi integral over x1 to x2 e to the power minus half x minus mu whole square x minus mu by sigma whole square dx. Okay. The integral f x, okay, f x equal to 1 by sigma root 2 pi integral over minus infinity to x e to the power minus half x b minus mu over sigma whole square dv, then gives us the cumulative distribution function of x. This is nothing but you can see probability that x is less than or equal to x. Okay. Probability that x is less than or equal to x is what? It is given by integral over minus infinity to x probability density function of x. Okay. This we know. So, this probability density function here is 1 over sigma root 2 pi. Okay. We are using here instead of x, we are using the variable b. So, we can write variable b here. So, we can write variable b here. Okay. So, integral over minus infinity to infinity f x v dv, and this is 1 over sigma root 2 pi integral over minus infinity to x e to the power minus half b minus mu over sigma whole square dv. Okay. This is called as the distribution function or cumulative distribution function for the normal variate. Okay. Now, if we put b minus mu over sigma equal to u here, okay, b minus mu over sigma equal to u if you put, then you can see dv by sigma equal to du. So, dv equal to sigma du, and the limits of the integration change from minus infinity to x to minus infinity to u equal to x minus mu over sigma. Okay. Hence, equation 3 becomes f x equal to 1 over root 2 pi minus infinity to x minus mu over sigma e to the power minus u square by 2 du, and this is a function of x minus mu over sigma. So, we can write it as phi x minus mu over sigma, and this phi x over minus x minus mu over sigma, then it becomes phi z, where z is the standardized normal variable. Okay. Z equal to x minus mu over sigma, as we have discussed earlier, z equal to x minus mu over sigma. So, x minus mu over sigma is replaced by z. Now, from 2 and 3, okay, from 2 and 3, from this and this, okay, let us see what happens. From 2 and 3 we obtain that probability that x1 less than x less than or equal to x2 is then f x2 minus f x1, because f x is the cumulative distribution function. Okay. F x is the cumulative distribution function, it gives the probability that x is less than or equal to x. So, f x2 minus f x1 will give us the probability that x1 is less than x less than or equal to x2. Now, so if you put the value of x2 here, then f x2 becomes phi x2 minus mu over sigma. So, probability that x1 is less than x less than or equal to x2 can be now written as phi x2 minus mu over sigma minus phi x1 minus mu over sigma. This can then be written as phi z2 minus phi z1. Which will be nothing but the area under the standard normal curve, okay, standard normal curve this is standard normal curve phi z, okay, from Z1 to Z2. Okay, phi Z2 minus phi Z1. Okay, this is the area under the graph of phi z from Z1 to Z2. So, the integral in this phi z represents the area. Remember, phi z represents the area under the graph, okay, of phi z. Where phi z is under the graph of the density function. Okay, density function is this. Let me write density function. Density function is 1 over root 2 pi e to the power minus z square by 2. Okay. So, this is the graph of 1 over root 2 pi e to the power minus z square by 2, okay, and phi z represents the area. Phi z is the area from minus infinity to z, okay, 1 by root 2 pi e to the power minus z square by 2 dz. Okay. So, phi z2 minus phi z1 gives this area, okay, under the standard normal curve. Okay. The integral in 3. Now, integral here cannot be evaluated by elementary methods. Okay. This integral, you can see this integral cannot be evaluated by the elementary methods that we know in integral calculus. So, it has been numerically evaluated and it is available in the form of a table. Now, it is given in all engineering mathematics standard engineering mathematics books at the end as an appendix. So, you can refer to that table to determine the value of this integral. Okay. Now, this integral has been evaluated for the standard normal curve, okay, for this curve, okay, 1 by root 2 pi e to the power minus z square by 2. That means, this phi z has been evaluated. Okay. This area under the graph of the function 1 over root 2 pi e to the power minus z square by 2 has been evaluated for any given z. You can take any given z here, then the area under the graph has been evaluated. So, that we can use, as we shall see just now when we do examples, how to use that table. So, we will evaluate the probability using that table, okay, for the standard normal curve. Now, from the table of phi, okay, from the table of phi, it follows that the area, or you can say the probability when x lies between mu minus sigma to mu plus sigma, okay, is 68%. This is your mean, okay, mean of the normal variate x, okay, this is normal variate x. So, on either side when you go to by a distance sigma, so then from mu minus sigma to mu plus sigma, 68% of the area lies under the graph of the density function of x. Okay. That means 2/3 of the values of x lie in the region between mu minus sigma to mu plus sigma approximately, and then from mu minus 2 sigma to mu plus 2 sigma, from mu minus 2 sigma to mu plus 2 sigma, 95.5% values of x lie. And when you take mu minus 3 sigma to mu plus 3 sigma, 99.7% of the values lie. That means about a 1/4% remain outside this region which lies between mu minus 3 sigma to mu plus 3 sigma. If you convert this to standardized normal variable z, then what it means, you put x minus mu over sigma as equal to z. Okay. So, this is same as probability that minus 1 is less than z less than 1, okay, and this is means probability that minus 2 is less than z less than 2, okay, and this means probability that minus 3 is less than z less than or equal to 3. So, from the table of phi for the standard normal curve, we have calculated the area which lies between z equal to minus 1 to z equal to plus 1, that area is 68%. So, that area is 68% for the normal variate x here. We have put the we have converted this z to this x here. Okay. So, from this from these areas we have concluded about the values of x that lie in those ranges mu minus sigma to mu plus sigma it is 68%, mu minus 2 sigma to mu plus 2 sigma, it is 95.5%, and mu minus 3 sigma to mu plus 3 sigma, it is 99.7%. Okay. Now, from from these inequalities, from these values it follows that a large number of observed values of the random normal variate x are distributed as follows. Nearly 2/3 of values lie within sigma of the mean, about 90%, 95% lie within 2 sigma of the mean, almost all values except about a 1/4%, okay, 0.25%. If you leave 0.25%, all other values lie between mu minus 3 sigma to mu plus 3 sigma. Okay. The z score of a value, okay, z is x minus mu over sigma, we call it z score. So, z score of a value from a random variable is the number of standard deviation away from the mean. You can see from the definition, z is nothing but the number of standard deviation away from the mean. By calculating the area under the well curve, this is well curve, okay, z, this is the curve for z, okay, standard normal curve. We have written here x for z, okay. You can see at x equal to 0, it assumes the maximum value 1 over root 2 pi. So, this phi x here is 1 over root 2 pi e to the power minus half x square, okay. So, this is 1 over root 2 pi. You can see that phi minus x is equal to phi x, okay. So, it is symmetric, okay, it is symmetric with respect to y axis, and the area under capital phi x, okay, gives the area under the graph of phi x, okay, minus infinity to x phi x. Note the difference between this phi and this phi, okay. This is capital phi, okay, this is capital phi, it is the area under the graph of this probability density function phi, this is probability density function phi x equal to this probability density function. So, under the graph of phi x from minus infinity to x. So, this area, okay, suppose x is positive, okay. If x is positive, then you can see because of the symmetry of phi x about the y axis, the area under the graph of phi x from minus infinity to minus x, okay, phi minus x is equal to 1 minus phi x, okay. If you want this area, okay, to obtain this area, okay, what we do? The total area under the curve is equal to 1, from 1 we subtract this entire area, okay. So, then we will get this area. So, this area integral over minus infinity to minus x, okay, phi x dx, okay, area under the graph of phi x from minus infinity to minus x can be obtained by subtracting the area under the graph of phi x from minus infinity to x, okay, because of symmetry, okay. So, now the distribution function, this is phi capital phi x, okay, which I have talked about here, this capital phi x, okay. So, this capital phi x is the cumulative distribution function of small phi x, okay. It is denoted by capital phi, given by minus infinity to x 1 over root 2 pi e to power minus half x square dx, and is the area bounded by the standard normal curve up to x, okay. This is the graph of standardized normal distribution, okay, this phi x, okay, this is the graph, okay. Now, what we do, let us go to first example. If the lifetime x of a certain kind of automobile battery is normally distributed with mean of 4 years. So, mu is given to be 4 year, okay, standard deviation sigma is given to be 1 year, okay, and the manufacturer wishes to guarantee the battery for 3 years. That means, he says that the battery will at least work for 3 years, okay. What percentage of the batteries will he have to replace under the guarantee? That means, we want to find the percentage of those batteries which will not last for 3 years, okay. So, probability that x is less than 3, okay, this is what we want, okay, and probability x less than 3 is equal to 1 minus probability that x is greater than or equal to 3, okay. Now, we will change this probability x less than 3, we will change this variable x to z, okay. So, x is equal to z equal to x minus mu over sigma. Okay, z equal to x minus mu over sigma. So, mu is equal to 4. So, z will be equal to x minus 4 upon 1. Okay. So, z equal to x minus 4. Okay. We want the probability that x is less than 3. Okay. Probability that x less than 3 means, okay, this x is less than 3 means z is less than z is equal less than minus 1, okay, because x is less than 3. So, this z is less than 3 minus 4. So, z is less than minus 1. So, this is equal to probability that z is less than minus 1. Okay. Now, let us look at the graph, okay, graph of the standard normal curve. This is standard normal curve, okay, 0, and z equal to, this is z axis, this z axis, okay, this is phi z, okay, the probability density function phi z. So, this is z equal to minus 1 here. Okay. As I said, the area under the graph of phi z, okay, from minus infinity to minus 1 can be found by subtracting the area from minus infinity to 1, okay, minus infinity to 1 from 1. So, this is equal to phi minus 1, let me write like that in terms of the capital phi function. So, phi minus 1, okay, this is equal to 1 minus phi 1. Okay. Now, let us go to the table, see the value of phi 1 from there. This is the table. You can see in this table, when z is equal to 1, when z equal to 1, phi is equal to 8.8413. Okay. This is the value of z and this value of capital phi z. Okay. So, when z is equal to 1, this is 8413. Okay. So, let us put that value there. So, this is 1 minus 0.8413. Okay. So, this is 7851. Okay. So, this means that it is equal to 15.87%. Okay. So, he will have to replace 15.87% of the batteries because they will not last for 3 years or more. Okay. So, so this is how we will use the area under the graph of the standard normal curve to solve the problems. Now, let us go to a specification for a certain job. Call for bolts with a diameter of 0.280 plus minus 0.002 centimeter. If the diameters of the bolts made by some manufacturer are normally distributed with mu equal to 0.279 and sigma equal to 0.001, what percentage of these bolts will meet specifications. So, specifications are that the diameter of the bolt should lie between this range. Okay. So, let us see, x should lie between 0.280 minus 0.002. Let us find the range of values. So, we subtract first 0.2002 and get here 872. Okay. So, 0.278. Okay. And then when we add 0.002 to 0.280, we get 0.282. So, we want the percentage of bolts which will meet the specifications. That means, we want the probability that the x denotes the diameter of the bolts. X denotes the diameter of the bolts. So, diameter if it lies in the range 0.278 to 0.282, then it is acceptable. Okay, it meets the specification. Now, let us calculate the corresponding values of z. So, z equal to x minus mu over sigma. Okay. So, we get z equal to 0.278 minus mu equal to 0.279 divided by 0.001. So, this is equal to minus 1. Okay. And z equal to x minus mu over sigma when x equal to 0.282. So, we get 0.279 divided by 0.001. So, this is equal to 0.003 divided by 0.001. So, this is 3. Okay. So, this is equal to probability that z lies between -1 to 3. Okay. Now, let us consider, let us look at the graph okay, again. So, okay, suppose this is graph. So, -1 is here, okay. This is your z axis, okay. This is your phi z function, okay, probability density function phi z. Now, this probability is we have to find. So, -1 to 3 we want, okay. This is 3 here, this area we want -1 to 3, okay. This means what? We find the area under the graph of the curve from -infinity to 3 and subtract the area from -infinity to -1. So, this is phi 3 minus phi minus 1, okay. And phi minus 1 can be found by subtracting the value of phi at 1 from 1, okay. So, phi 3 minus 1 minus phi 1, okay. So, what we get? Phi 3 plus phi 1 minus 1, okay. Now, let us see the value of phi 3 and phi 1 and then we will add them and subtract 1. So, we can see here the value of phi 3, okay. Phi 3 is 0.9987, okay. This is 0.9987. From here you can see phi 3 is equal to 0.9987, okay. And phi 1 we had already seen, phi 1 equal to 8.8413, phi 1 equal to 0.8413, okay. So, let us use these values. So, 0.9987 plus 0.8413 minus 1, okay. So, how much is that? 7 plus 3 0, 10, 1 carry out, we have 9, 1 0 and then we have 100, 184, okay. So, 1.8400 minus 1, okay. So, 0.84, that means 84% of the bolts meet specifications, okay. So, 84% of the bolts meet the specifications. Now, assuming the resistance of the resistors to be normal with mean 100 ohms and standard deviation 2 ohms, okay. What percentage of resistors will have resistance between 98 and 102 ohms? So, we have, let us say X denotes the resistance of the resistors, okay. Let X denote resistors, okay. Then we want the probability that X lies between 98 and 100, 2, okay. So, this is equal to probability that Z lies between the Z is equal to X minus mu over sigma. So, Z will have the values 98 minus 100 divided by 2. So, that is equal to minus 1, okay. And when X is 102, it is plus 1, 102 minus 100 divided by 2. So, plus 1. So, the Z lies between minus 1 and plus 1, okay. So, now what we will do, let us see, okay. So, this is your minus 1, okay. This is plus 1, okay. We want the area under the standard normal curve from minus 1 to plus 1, okay. So, what we will do? We will find the area under the standard normal curve from minus infinity to 1 and from that we subtract the area under the standard normal curve from minus infinity to minus 1. So, this is phi 1 minus phi minus 1, okay, and phi minus 1 we know is 1 minus phi 1. So, phi 1 minus 1 minus phi 1, okay. So, this 2 times phi 1 minus 1, okay, and we have seen phi 1 equal to 0.8413, 0.8413. So, we can use this value here. So, 2 times 0.8413 minus 1, okay. So, this is 1.6826 minus 1, okay. So, this is 0.6826, meaning that it is 68.26%, okay. So, 68.26% resistors will have resistance between 98 ohms and 102 ohms. Okay. Now, we go to this last question. Sacks of grain packed by an automatic loading machine have an average weight of 114 pounds. So, so here we are given mu equal to 114 pounds. It is discovered that 10% of the bags are over 116 pounds. Find the standard deviation. We have to find sigma, okay. We have to find sigma here. We know that Z is equal to x minus mu over sigma, okay. We are given that probability that x is more than 116 pounds, okay, is equal to 0.1, okay. This is given to us, that 10% of the bags are over 116 pounds. X denotes the weight of the bag. So, probability that x is greater than 116 is equal to 0.1, which is given to us. So, Z will be equal to, let us see the corresponding value of Z. So, Z will be equal to 116 minus 114 divided by sigma. So, 2 by sigma, okay. So, probability that Z is greater than 2 by sigma is equal to 0.1, okay. Now, we have to see from the table that where for what value of Z we get the probability to be 0.1. You see, let us look at this, okay. Suppose this 0.1 is the area, okay. So, suppose this value of Z, okay, and Z is greater than 2.2 by sigma. So, this area is given to us, okay. We want to find the value of Z for which the when Z is greater than 2 by sigma, okay, Z is greater than Z naught. Suppose this is Z naught, okay, this is Z naught, okay. So, when Z is greater than Z naught, the area becomes 0.1. So, that means that the area to the left of Z naught, okay, suppose 2 by sigma is Z naught, okay. So, we want this area is 0.9, okay. So, let us find the under the graph of standard normal curve for what value of Z naught, okay, we have the area 0.9, okay. So, let us go this one. So, here you can see this is I think 1.26, 1.26 gives you the area close to 0.9, okay. So, we have let us take so Z naught is 1.26, okay. So, then this is or you can say probability that Z is less than or equal to Z naught, okay. Z naught is equal to 2 by sigma, okay, is equal to 0.9. So, then we obtain Z naught equal to 1.2 sigma. So, Z naught equal to 2 by sigma gives the implies that 1.2 sigma 2 upon sigma equal to 1.26 or sigma equal to 2 by 1.26. So, how much is that? This is 200 divided by 126, okay. So, what do we have? And then we have 1.28, 1.28. So, 2 over 1.28, okay. So, we get, okay. So, 1.5625, okay. Let us put the exact value, okay. So, what we get is 1.5625, 1.5625. So, the standard deviation is 1.5625. Okay. So, with this I would like to end my lecture. Thank you very much for your attention.